Okay, let's start. So we are now more or less done. So what this is the status. We have introduced the one-step theta method as the most simple one-step discretization which is feasible in conjunction with the discretization of parabolic initial boundary value problems. And we are doing the two necessary and typical steps of analysis, or three: stability, which is often underestimated in its importance; consistency, this we do explicit or implicit depending on the type of the method; and finally, of course, convergence and order of convergence. And what we have seen now, on the one hand side, if we have stability in an norm which is related to the discretization matrix in an energy norm, then we can transfer this. We know how to describe stability of a one-step method, and what are the consequences then for the corresponding estimate without time discretization. So we are now in the other version is to look at other norms, namely L-infinity norms, and this we can do by going in the direction of the validity of a maximum principle and the various variants of it, which in the end, as we have seen already in the very beginning with finite difference methods, allows us to have stability in L-infinity. So we are in the process of looking at that. And I will hopefully finish this now soon, and then on top of that discuss the outcoming stability, the outcoming order of convergence estimates for the different versions we have now. I'm not sure whether we can finish this today, but we will more or less finish this so that we still have 2 dates then left. So either we have to finish this aspect, but at least we have some time left to look at least at very simple versions of nonlinear problems then. So of course we have to be aware that we are very much in the realm of toy problems at the moment, and usually problems one wants to solve in reality look a little bit more complex in very many aspects. But of course we have to set a foundation. Maybe in this conjunction I should point out that there are 2 courses next semester which might be or hopefully are of interest for you. That is the continuation of this course. So there is a part 2, which is, again, if it is demanded from the audience, it will be in English. The major context is to go now a little bit away from the, so to speak, diffusive dominated processes more and more to convective dominated processes. And we know already that the finite element analysis and also the finite element idea comes then a little bit to its end. We are then coming in the situation that the alpha in the ellipticity estimate goes to 0, and of course that would mean we have all our estimates which we have, but they would all be have astronomic constants in front of that. And in numerical practice, this means that these methods, in the way we have it right now, are of no use anymore. They are still convergent methods, but of course, nobody can afford to really compute up to the domain of convergence. So we need other. And there's also, of course, a clear physical background behind of that. Our discretizations are undirected in some sense. They are based on central differences, but convective processes are directed. And if you remember, we have seen already the most simple and most important cure in conjunction of finite difference methods, where we said, okay, we have this convective part. It is maybe a good idea. It seems to be a good idea to take the central difference quotient because it has second order, but it turns out that then, because of this undirected nature, we, for example, we need further strong assumptions to preserve the good matrix properties, the matrix properties underlying the maximum principle. This led to conditions with a Peclet number, with a cell Peclet number. The cell Peclet number has to be small, but if the Peclet number of a problem which measures the relationship between convection and diffusion is big, say 10,000, which is a typical number, then this really means one has, again, compute with very, very small spatial discretizations. So there are remedies. That was the upwind discretization, and in this direction the thought should go on. And of course, at the end of the line is, so to speak, the problem with Peclet number infinity, that is pure convection or pure wave propagation. And that is one line of development, and the other line of development is, of course, to bring more nonlinear problems in, which we have not seen too much up till now, and of course to discuss that next week will not be sufficient. So that is the idea for the second half of this course, and you can, if you are I'm not 100% sure how it is for CE students, but I think they can use that also as in their mathematics part, and the mathematics students can use this both in bachelor and in the master's program. And the similar thing applies to the course, which is also a 2-hour, so this is a 2-hour lecture course, and the 2-hour lecture course offered by Professor Serge Reutle. And this is first thought of as being a German lecture, but of course this can also be changed to an English lecture. And the German official title is, I think, is Transport and Reaction in Porous Media. And this is, it's not strictly connected to each other, that the one is not accessible without the other, but it's sort of a first part of a second part, two-part enterprise, and this first part looks at modeling. I think that is more or less the official title. So this relates to now, so to speak, to bring everything what we did, and now more not so much the numerics part still, but more the things we talked about. What is in PDE, where it comes from, and so on. What kind of properties does it have in the realm of a important application? So transport means now both diffusion and convection. And the problems become nonlinear because this is now not only one substance, one species, but there are many, and they react in different ways. So this goes in various kinds of technological and, so to speak, the whole field of chemical engineering is sort of contained here, because that is what a chemical engineer does. But also there are applications in the natural sciences, in geology. So this would give some introduction to use of mathematics in an application field. So there is, I'm not sure whether there's already a date fixed. The date is, of course, can be adopted later on, and that same applies to the second part of this course. I think there's a date fixed at the moment. As far as I know, Monday at some time, Monday afternoon. But if it turns out that this is not a good date, this can be changed also. Okay, so now let's go back to the discussion of the validity of a maximum principle, and I've reminded you here again the conditions we have to see for a matrix such that variance of a maximum principle hold, which is in its basis the sign conditions. The sign conditions and the sum conditions, irreducibility or some weaker forms, and then some further conditions relating to the influence of the Dirichlet data. And we are now in the process of saying, and we had collected again these conditions a little bit and reminded us what kind of consequences they have. So the first question is the inverse monotonicity of the matrix. That is the most basic question. And for the inverse monotonicity of the matrix, we need the sign conditions 1, 2, 3, the first half of 3. The second half is sort of related to Dirichlet data, as we have discussed last time, and 4 star, that's a weakening of this irreducibility condition, as we discussed last time. And if we go on and we would like to have a comparison principle, so we have to include also the Dirichlet data, not only the distributed right-hand side, then we need this condition 5, which is, so to speak, the discretization matrix part, which acts on the eliminated Dirichlet data, and that has also have to have the right sign. And if we go on, then in the end, we can if we go on with the conditions, we can get maximum principle and even strong maximum principle. But we have seen the real thing, what we need in conjunction with this question, how do I come from consistency to convergence, is the comparison principle. Because consistency means the error fulfills the equation with a right-hand side, which is just the consistency error. And so if we can estimate this from below and above by certain terms in a power of h, which is the consistency error, that means we can, this then transfers to correspondingly to the solution by the comparison principle. So we are asking now us the question, how is it if we now say, okay, our spatial discretization is such that those conditions, or a collection of these conditions, is fulfilled. We have a spatial discretization which fulfills a maximum principle or a comparison principle, either a finite difference discretization, where we have seen how this comes in, or a finite element discretization, where in the pure diffusive, in the case of the pure Poisson equation, we also have seen that it holds true if we have the right conditions on the triangulation. So this is the abstract starting point, and the question now is how does it transfer to the parabolic situation with this spatial discretization and the theta step method as the time discretization. So we put all the solution at each time level together to a long vector, and we write formally, of course we do not do that computationally, formally everything what we do into a big system of equations, which is upper triangle, a lower triangular matrix, which just says to go from the to the second time level, we only need the zeroth time level, so only data. To go to the second, we only need the first, and so on. Obviously, this matrix is non-irreducible, so we have to rely on this weakened condition. And this would be then the right-hand side, which contains here parts of the initial data at the first time level, and which contains the distributed data, and the distributed data again are subdivided into the part which comes from the distributed source and the part which comes from the elimination of the Dirichlet boundary condition. And contrary to the situation in the pure stationary case where we needed some Dirichlet boundary condition, we don't need it here. So in principle, this whole part might not be here. So this, I did not want to explode the notation, so, but this is a possibility that there are no Dirichlet data. Okay, so we started in, and the fixed data, the Dirichlet data, they now include also, because there's also now a fixed datum, the initial data. And this is the key why we can deal with pure Neumann data, because we have already a part of Dirichlet data in terms of, formally spoken, in terms of this initial data, which we always have. Now, if we go through the conditions, so in the end, what comes out is that the right-hand side has the following structure. This is the part which comes from the distributed source, and there's a part which, this is, so to speak, the analogous notation as before. Now, the matrix is called C instead of A, but all the tildes and heads and so on are meant in the same way. Here the corresponding Dirichlet data go in, and here the initial data. So that means if there would be no Dirichlet data, this matrix CH hat would only consist of this part here. And everything else would be zero. So we now post one condition which at the first glance seems a little bit astonishing, or maybe also disappointing. And it's not often noted in textbook in this clarity, I would say, that one needs something like that. It is this condition, which says tau times the diagonal elements of the spatial discretization times theta bar must be less than 1. That means in the case of the implicit Euler method, so to speak, in the most important case, there's no requirement whatsoever. But in the second most important case, in the Crank-Nicholson case, which one would also, of course, would like to do because of the expected higher order of convergence, this is a requirement. And we discussed already, because in this AH we have something like 1 over H square. It is, in fact, it's again a bounding condition on the quotient tau over H square. It is similar to the bounding condition which we have seen for the explicit time-stepping method, but it comes here from another background, from stability in different norms. Of course, the L infinity stability is, of course, a sort of a more strict stability than an L2 stability. So we now check under this condition what about the matrix condition. And we have seen the first one is okay. I have to see how I can do this with 2. The first one is okay, with the sign conditions are okay. Here the first is no problem whatsoever. The second, there the condition goes in, but only in a weakened form. The third is also okay. And now we have to come to the what is now not here on the transparency, the 4 star, to the weakened form of the irreducibility, which basically meant for every nodal point which has the property that the sums about which we are talking, where are the sums about which we are talking here, are positive, meaning that we are sort of close to the boundary. They have to be, sorry, maybe I should, it's the other way around. Every point should be connectable to a point, in particular a point where the sum is 0, should be connectable to a point where the sum is positive. So we have to find a path to the corresponding adjacency matrix, so a path along indices where the corresponding matrix entries are non-zero, such that we come from any point to a point close to the boundary. What does now mean close to the boundary? What is the possibility? So this is this condition. If we have this situation, we would like to connect to a point where we have this situation. So how is this situation characterized? That means in these stencils, something has gone, so to speak, to the other side, to the right-hand side. That the reason for that might be, as we have seen already, just a Dirichlet boundary condition. But the reason might be also to be close to the initial data. And therefore, and I don't want to overdo this now, so we know if we now use the same notation as we did before, the notation far from the boundary, close from the boundary, and again related only in algebraic conditions to these to some requirements, then we see all points of the first level are close to the boundary. We see this purely algebraically, and of course also the Dirichlet boundary. Let me put it in another way, in a more formal way. Those points are close to the boundary. Points are now always, of course, space-time points, where the spatial point is close to the boundary with respect of the underlying spatial discretization matrix, meaning where the corresponding sum here is positive. But this also corresponds to, so to speak, our geometrical imagination of the problem. Let's think of the space-time cylinder. And then, of course, close to the boundary might mean close to the mantle. That would reflect the Dirichlet boundary condition, and close to the 0 level. That would reflect the initial data. So all the things come together, but we can argue purely algebraic. So we can say, I don't know, I have no idea what I'm doing here, I have no imagination what a space-time cylinder is. The only thing I have to look at whether the sum is positive or 0, and then it also comes out. Okay, so how to find the way now? So what we have to show now that for every point it's possible, every space-time point is possible to find such a path in the adjacency matrix to a point close to the boundary. One possibility is to do this just if this is the case, and if there are Dirichlet boundary conditions, one possibility is to stay, so to speak, in the same time level. And to go within this time level the same way as we did it and argued in the stationary case, to go, so to speak, step by step for the same time level, step by step, spatially spoken, up to the boundary. And this has to be possible, of course, and this is possible if the corresponding condition holds true for the underlying spatial matrix. So this is set here. We can do this if the matrix AH also fulfills this requirement. The other possibility would be, okay, we stay where we are in space, x stays now the same, but we move in time. And we would like to find our way down to the zero, to the initial data in the cylinder. So now what kind of requirements do we need? And this is also possible under our assumptions, and for that we look again at the matrix. So what we have to do is we stick at the same point and we go back in time. So what we have to need is that the diagonal entry here, this is now reflects the situation one time level lower, but at the same time, that the diagonal entry here is non-zero. And this is exactly where this condition comes in, because this condition just says the diagonal entry is strictly negative. For the sign conditions, we would have been done by less or equal to 0, but really to do this path argument, we really need, and I go back, show it to you again, where is it? Oops, where is it? Here, we need this strictly less than 1. This makes this diagonal element, this is just this thing minus 1 strictly negative. So that would be the other possibility. This is noted here. So to summarize, how can we satisfy this requirement, this this relaxation of the irreducibility? The first possibility is we have it for the AH, and the other possibility is we go down to the initial data because we know that the diagonal element of this matrix does not vanish. Okay. The rest is now more easy to look at. We need to have the corresponding sign condition for the matrix which deals with the Dirichlet data. If there are any, this is again brought back to the corresponding condition for the Dirichlet part of the spatial discretization. And we have to have that if we go over the full rectangular matrix for this condition 6 star, that the sum is 0, and again this is fulfilled if the same condition holds true for the spatial discretization. And okay, there's there's still one thing, and correspondingly, if we only want to have that the sum is non-negative, we need to have that the corresponding sums for the rectangular spatial matrix also has this property. So it goes over, or everything goes over directly. And then there is still this property which says that the data have to enter in the sense that it really should influence the. That is not important for the comparison principle or for the weak maximum principle, but that is of importance for the strong maximum principle. Of course, then it cannot be allowed that we have initial data which do not influence the solution at all. Then, of course, it would be possible that the solution has maximum in the interior and is not fully constant on the whole domain, because there's no reason why it should take this same value on this totally isolated node. But for the weaker forms, we do not even need this, as we have seen in the before, but also this is also satisfied here directly. So let's summarize what we have seen. So we look at the theta step method, and we assume that this condition 625, that was exactly this condition, theta bar times tau times jj is less than 1, is satisfied, and now we need to assume that the underlying spatial discretization fulfills condition, where we are, condition 1, condition 2, the sign condition, condition 3, 1, this is this first line, the sum non-negative, the negativity of the sum condition. This part is not necessary, so we do not need to have any Dirichlet boundary conditions. And condition 5, nothing about irreducibility or nothing about connectivity in this weaker sense, because we can always solve this problem by not going to the Dirichlet boundary. We cannot do if there's none, but we can always go down to 0 to fulfill this 4-star condition for the time-space situation. So this is just what we need, and then we have a comparison principle. In the sense, still the condition 5, of course. That means also the part, the AH hat part, has to have the right sign. And then we have a comparison principle in the sense if we have an ordering in the data, if an ordering in the initial data, and in the Dirichlet data, if there are some, then there is an ordering in the solution. Okay, this is now a general statement that applies for finite difference discretization, but it also applies to corresponding finite element discretizations. Let's assume that we have a finite element discretization with, say, flux boundary conditions. Where do the flux boundary conditions enter, and do we also have a sort of a comparison in flux boundary conditions? Where is this hidden? Where is the flux boundary condition term hidden in the finite element case? Or is it not allowed? Do we have to have 0 flux boundary condition? If we would have 0 flux boundary condition, we know we would not see them in the equation. They are the natural boundary conditions. Now let's assume we have inhomogeneous flux boundary conditions. Where do they appear? In which of these letters? Or maybe they do not appear? Bitte? Hier? What's the Unterschied? Ach so, okay, this is a misprint, of course. This is a misprint. Of course, it's not wrong, but of course it's a misprint. It means the U. It means the solution, the full solution. This is the Dirichlet data. This is the Dirichlet data. This is the initial data. Okay, here, of course, there's also a misprint. I'm sorry, I don't see these misprints because I expect that the right thing is there. But of course, you're absolutely right. It's a condition you might assume that it holds true, but it will not give you too much if this would have been meant here. Okay, of course, it's just as I said, we have an ordering in the initial data, an ordering in the Dirichlet data, so there's a 2 here, and then that is the assertion we have an ordering in the solution, so there's no hat here. interesting. Why is this? Is this also in the book? Must be. Yeah, you should correct it. Okay. I've read this 10,000 times, but I don't see this. That's okay. Of course, if we have the same Dirichlet data, then we do not need this condition 5. But now back to my question. What about flux data? Where are they? Are they allowed? You've implemented it, haven't you? Where are they? In the F. In the F. The F consists, in the finite element case, the F consists out of the integral over the distributed source and the test functions. And that again shows us that this corresponding pointwise inequality, this only formulated here algebraically for the vectors. Of course, a sufficient condition is then at least, we have to be careful, at least in the case of linear elements, that we have the same pointwise ordering for the underlying functions. And if we have inhomogeneous flux boundary conditions, then in addition, then there are integral parts with this corresponding part times the test function. So the important thing is that the test functions, that the nodal basis functions are positive, that we can. So it's a condition, of course, which involves the Dirichlet data. The flux data, which involves the distributed source. But if we want to break it down to the more natural condition and say, I have a pointwise ordering between the distributed sources and I have a pointwise ordering between the incoming flux. Of course, I expect if my incoming flux is stronger, then my solution should become larger. So it should be a requirement on the incoming flux, monotonicity in the incoming flux. Then we want to then we have to make sure that the nodal basis functions are non-negative, and this we can only assure in the linear or multilinear case. In the case of higher order elements, it might well be that the basis function drops down. So if you maybe you have an idea how a basis function, say in 1D, looks in the quadratic case, and so it has a 1, a 0, and a 0, but it is on the two intervals which belongs to its support. But as the parts are not linears, but they are quadratics, the quadratics may go below 0 or will be. So there is a little bit of a problem, but how to relate this then in not so in terms of the underlying data for higher order elements, but in principle it's also possible for the finite element case, and it's all included here. In the finite difference case, all these problems do not come up. In the finite difference case, these data are just evaluations of the right-hand sides, but we have seen in the finite difference case we also have a very, very hard time to include flux boundary data. Okay, so and now we can go on. We can also show a weak maximum principle in the sense that we hopefully now it's better here, it's not so full of misprints. So what do we have here? We have here now the full solution, including the possible Dirichlet data. This is the tilde. We go over all time levels. We go over all spatial points here. And this maximum can be estimated by the maximum of the initial data and the maximum of the over all time levels in addition here of the Dirichlet data. And what we need in addition, that's a consequence of our discussion, we need to have that now the underlying spatial discretization has to fulfill this weakened irreducibility condition. And if we have the full irreducibility condition, and if in addition we have this condition 7, which says all Dirichlet points enter, then we really have a strong maximum principle in the sense if there is a non-negative maximum in the interior, then the whole solution has to be constant. But for the further conclusions to deal with now the order of convergence, this comparison principle, of course, in the corrected form, is of importance. It's not really wrong what it's... No, it's wrong what it's stated here, because from this I cannot conclude this here. But okay. So this we said already, this condition which we need to have in the case theta non-equal to 1 is really something like a stability condition as we have seen it. And now we can go over to the order of convergence estimates. Okay, we start with a finite difference case and then do the same thing too for the finite element case, and most probably we will only deal with the finite difference case today. So here we are now back to our very beginning, and we know what we have to do. Everything what we are doing, let me first... There is somewhere, it comes later. Okay, let's go through it. So we have to have an estimate of the consistency error. That is the basis of it. And then we have seen how to deal with the with the maximum on the basis, how to derive a stability estimate on the basis of on the basis of this comparison principle and of the on the basis of having an inverse monotone discretization. Okay. So you might think now in the following of the pure Neumann case, but this is not really necessary. So to fix a little bit the notations, so we have grid points, of course. They might be in omega h or also in omega h bar if we not only have Dirichlet data. And then we have to consider the solution at some instance of time, which is typically one of the time steps, Tn. And so what we have to do is, looking at the consistency error means we take the real solution, plug it into the scheme, and then something comes out, the consistency error. And that is the quantity we have to estimate. And to estimate this quantity, we need, as we have seen already, an enormous amount of regularity on the solution. So we have discussed this once, we do it, so we just assume what we need, and we know that this is not a good assumption. So for the notation, what is this capital U means, take the exact solution at the time t, evaluate it at the grid, and you get the grid function or correspondingly the representing vector out of that. So that is the amount of points we are working on, depending whether we have only Dirichlet or also flux or mixed boundary condition. That is the quantity we would finally like to estimate. So we would like to estimate a norm of this vector error grid function exact solution minus grid function discrete solution at the time level n. And as I said, the consistency error now comes to existence if we just take the exact solution and plug it into our scheme. And the consistency error vector is now here denoted by q hat n plus n, and here this is the formula how to compute it for n plus 1. So this exists at each time level. And what the relation, of course, now is if we multiply, if we plug in not the exact solution, not only the exact solution, but also the discrete solution in the discrete formula for the discrete solution, this gives us 0. Everything is linear here, so in the end we have here as a right-hand side the consistency error. In the stationary case, we just had something like here matrix A times error. So the only stability question there was, what is about the norm of the inverse of this matrix in the corresponding norms induced by the maximum norms. And this was something which we could handle in terms of those things we discussed right now. Now our operator is a little bit more complicated, and it's, so to speak, it's the full operator which goes through. If we plug in all these things for going through all the time steps. More precisely, exactly the large matrix CH we have put on. But in principle, it's the same stability question with which we have dealt already in various versions. We have certain driving forces. We have nothing in the initial data, assuming that as what is reasonable in the finite difference case that we start exactly, that we take the exact initial data and evaluate it at the grid. If we would not do so, if we would take any other vector to start with, then the corresponding error would appear here. And we have a driving force which is just the consistency error. Now again, the stability questions which we have so to speak, evaluated already to some extent. Also here in this situation comes up saying, now what happens? What happens if we have here perturbation sources? What is the corresponding estimate for the solution? Verdammt nochmal. Moment. Knabner, bringen Sie mal bitte meine Flasche Wasser runter. Okay, and now so it depends, of course, now on the norm we would like to see this stability, and in the end, as a consequence, then the order of convergence. What kind of norms we have at our disposal? The norms with which we will work right now in conjunction with the maximum principle, as we have seen already, are the full maximum norms. Full means maximum in space and maximum in time. So that would mean to work with norms like this here. So we have the maximum over, we go in the maximums both over the time levels and over the spatial points, or we form a maximum of the maximum norms. We form a maximum in time over the maximum norms in space. A shorthand notation for this kind of norm is also L infinity, L infinity. where we always start with the time. So it's L infinity 0t, L infinity omega h if you want. On the other hand, so what is the other extreme, or extreme, okay, the other end of our scale is this norm. What does that mean? For each time level here, we have here the discrete L2 norm, more precisely the square of the discrete L2 norm, and these square values we sum up and multiply now with tau. So we apply the discrete L2 norm, so to speak, twice. First in space, and then in time. And this is what we now, in extension of our old notation, we can call now 0h, opposite to the infinity here. And here one would speak of an L2 norm. L2 0t, L2, and so on. And of course, there's also the version in between. So what is the relation between these two? In the continuous situation, of course, we know that the L2 norm is the stronger norm than the L infinity norm is the stronger norm than the L2 norm. That we can estimate the L2 norm by the L infinity norm, but not vice versa. And we would expect that the same holds here true in the discrete case. And this is the situation if we have a reasonable assumption on the discretization. Namely, if we know that the amount of points we are dealing with here behaves like h to the minus d, this basically means we have some sort of a uniform, or we know for uniform grids this is true, then we can do this, then it's quite obvious. Then here we can go here to the maximum norm, then we have factor m1 hd adds together to a constant, and then correspondingly tau times n adds together to a constant, namely capital T, and then we get an estimate of this type here. So then we have the same situation. So in principle we can say, of course, also in the discrete level, the L2 norm is the weaker norm than the L infinity norm. Okay, and then there are also the situations in between, in principle two, but only one will show up in the following. Of course, we can change trade one of the L2 norms for an L infinity norm and vice versa. So we would have the versions L2 L infinity and L infinity L2. And the version which will come up in our situation is the L infinity L2 version. So we measure in space with L2 and in time for each time level, that means in L infinity. So, okay. So now let's have a look at the consistency error. And so there are two things, so to speak, involved in the consistency error, why there is a consistency error. The consistency of the spatial discretization, of course, as before. The fact that what we are doing here is not what the exact operator is doing, the exact spatial operator is doing at this corresponding intermediate level. And on the other hand, there is a temporal consistency error, or a consistency error by the temporal discretization, because we have substituted the time derivative by this difference quotient. So if we plug in this term again cancels with this term for the exact solution. Let's go back have a look what the consistency error is. We have to argue a little bit differently. So we have this part, and here we have, so to speak, the right-hand side. The right-hand side is the evaluation of the exact right-hand side, and this is, so to speak, the exact differential operator evaluated at the corresponding grid points and the corresponding spatial points. So this Q can be substituted by these two terms, and that now means that this splits up the error in the temporal part, called S1, and in the spatial part, called S2. So the S2 part is more or less the same thing as we had before. What we looked at before was AHU minus L of U, basically. And now there's one slight difference, namely we have here a convex combination and here the evaluation at a corresponding time level. So that is basically, here now, here we expect that exactly the same spatial orders of convergence come out. And here we expect the corresponding order of convergence in time. So to do so, we assume that the solution is smooth enough, the exact solution is smooth enough that we have these consistency error estimates for the spatial difference approximation. We assume that we have the validity of such an estimate. So for each level in time, the solution should be so smooth that the corresponding consistency error, so this is the same thing here, this and this, but this is now evaluated at the grid, should fulfill this estimate here. This requires a certain regularity of the solution to get a certain amount of alpha here. And for example, for the 5-point stencil we have seen, we get alpha to 2 if we invest regularity CP of 4. This is very high, but I don't want to discuss this now for the 10,000th time. So this is our assumption, and let's see what we can do with this assumption. Okay. In the case theta equals to 0 or theta equals to 1, then we are more or less done by this. Then this part just reduces to our assumption. And in the general case, in particular for Crank-Nicholson, that's more or less the only important case in between, we have to do a little bit. Do a little bit means we again subdivide this error S2, this spatial error, in two parts, in the sense that what are we doing is we have this part here, evaluate at the intermediate time level. We introduce this part here, take the corresponding convex combinations of the two time levels, and then we have to eliminate these two parts again, so they appear with a negative sign here and correspondingly here. And this gives these two splittings. That means what we have here the consistency error according to our assumption in a certain convex combination. It's clear that this part S3 now just behaves by assumption like h to the alpha, and this S4 is something we have to look at still. So here we do Taylor expansion in the following form. Okay, this is just the normal form of the Taylor expansion with the Lagrangian remainder term here. So, so we do the Taylor expansion for this part here, one around Tn and one times around Tn plus 1. And if we plug this together, I don't want to do now the calculation, but this is, I think, quite elementary. Then we get a formula for this convex combination we would like to have. it relates to this quantity we would like to relate, and then we have an error term which is of order tau square, like this here. That means, by means of this, says this term here in addition brings in an error term of the order tau square. Of course, it requires second derivatives of the functions or boundedness of second derivatives, the functions we are dealing with, where we would like to apply this. We would like to apply this to L of u. So we need, say, continuity of this and this derivative. This is now more than we had in the stationary case. Of course, we had no time derivatives there. It's again the old disease of the finite difference method that we need enormous amount of regularity for the solution to say something theoretically. It doesn't say that the method does not work without these conditions. It only says we do not know it exactly. Okay. Now the other part, the spatial part, the first part I said already, this is just then directly given by our spatial assumption, so that's it. So we are done with this part. So the one thing what we still have to deal with is now the part S1, which deals with the discretization error which comes in by the temporal discretization. And we know here it is reasonable to distinguish between theta 1/2 and not equal theta 1/2, because in the case theta 1/2 we expect here an estimate of tau to 2, and in the other case of only of 1. And that is our old, so to speak, error estimate for the one-sided difference quotient and for the central difference quotient. So be very precise, we have done this proof only, so to speak, for the three cases: 0, forward difference quotient, 1, backward difference quotient, 1/2, central difference quotient. And the general case, again, has to be done by Taylor expansion, taking these two situations into account. So in the end, what we get here is, for the remaining part, for the temporal part, this tau estimate as we have expected it. So to summarize, what we have here is we have an estimate in the one-step theta method in the discrete L-finity norm for the consistency error of an error term which comes from the spatial discretization, the alpha from the spatial discretization, and tau beta equals to 1 or to 2, depending on the theta. Now, of course, this is now in the infinity norm. Of course, one could hope that one can gain something if we reduce the norms. If we reduce the spatial norms, for example, to the L2 norm, giving us in the end not an L-infinity estimate, but only L-infinity L2 estimate, then of course one could hope to increase here on the order of convergence if one goes away. We have seen these problems going away from the 5-point stencil, having first order terms, then the order of convergence drops down, and so boundary conditions and so on. Okay, so that is the stability we have seen here. So what is the status which we have? We know the error which we want to estimate in the end fulfills again a discrete evolution equation as given here by our spatial and temporal discretization, and we have an estimate of the right-hand side. And now the question is how we can go from this estimate of the right-hand side to an estimate of the solution, that is to the stability question. And the stability question, in one sense, we have dealt already with. Maybe I can go back and we see this. Not sure whether the English transparencies concerning stability are here, but they should be. That is this situation. It tells us, it's basically this estimate which tells us if we have a stable in time discretization, stable in the L2 norm, in the discrete L2 norm, then this stability goes through in this sense. And now here, that would be one estimate we can apply, and we will apply later on, just to look forward a little bit. Then here not the U would be here, but the error, and here we would correspondingly have, that is now not 100% correct because, yeah, okay. But here would be the corresponding consistency error, which we just have estimated. Okay, so, but concerning the L infinity now, so let's state this here. So what does this theorem says? So we apply the one-step theta method. So this now does exactly what I just indicated. We rely on the validity of this stability based on the existence of a basis of orthogonal eigenfunctions with eigenvalues lambda I greater or equal to 0. So we can allow for the 0, we can allow for the pure Neumann case. If we then have a consistency error in space of order alpha, then if we have stability of the method, either because it's astable or we have a corresponding step size restriction, and then if all these regularity assumptions are fulfilled for our consistency estimates as we've done it right now, then we have an order of convergence estimate in L-finity L2. So we have to underlie the L2 norm in space where we have had where we can deal with the stability. Okay, if we have estimated, so we need a corresponding consistency estimate in this norm. We have seen we can get it in the finite difference case, for example, even in the infinity norm if we invest enough in the regularity, and then the stability estimate tells us this now turns over from the estimate of the consistency error to the estimate of the error, and this is an estimate in L infinity L2. And the order is exactly what we have invested. We haven't lost anything. Now, where is the smoothing? We have seen smoothing effects in these parabolic equations. Where is here the smoothing effect? There's not so much of a smoothing effect, but there is a little bit of it. Namely, the point is that I'm not going now back again to all this transparency before, but I hope you remember it a little bit. What we had there on the right-hand side was something like sum over the norms of the Q's. So sum means that is a discrete L1 norm. Sum over h or let's say tau, we're speaking of time, tau times sum over the squares is the discrete L2 norm squared. Tau over the sums of the norms without a square is the discrete L1 norm. It's just the approximation of the integral. So what we have had is, what we actually need is, we need an estimate. We have done here much, much more with this a little bit crude argumentations with Taylor expansions and so on. We've done much more in the sense that we've done everything point-wise in L infinity, L infinity. But what we really need for this kind of estimate is a stability, is a consistency error estimate in the L1, L2 norm. Integral in time, sum in time, and then only in the corresponding then spatial norm, which has to do with the eigenvalues. So this is a little bit of a sort of smoothing effect in time. So we go from this L1 in time to an L infinity in time estimate. This is this improvement we get by the equation. But as we discussed already, and that is quite clear because we allow here for the zero eigenvalue, we have no exponential damping here. There cannot be one if there is lambda equals to zero eigenvalue. Okay. Now let's do the step on the basis of the inverse monotonicity. And okay, what was the situation there? I discussed it already a little bit, but I think it was probably a little bit confusing. So maybe remind ourselves what the situation was. So in the pure spatial case, in the stationary case, so we had a discretization matrix which was inverse monotone, which led to a comparison principle. So these type of conditions. So this is inverse monotonicity. How was the argument now to go by this and the corresponding consistency error estimate in L infinity to a stability result? And the point was what we needed is we needed a vector sequence of vectors WH with this property here, such that it is, so to speak, a super solution of the right-hand side 1, and on the other hand, these quantities, the discrete L infinity norms, where we could bound uniformly. We've also given an argument that we can always find such a vector sequence for discretization steps small enough under these assumptions here. So this is the basis for the L infinity, because this now produces us the corresponding comparison function. Because if we have this here, we can again multiply here with a certain constants, and then we get constants here. And the constants can be the bounds we get for the error. Something, if we have the consistency error, if we have an L infinity estimate for the consistency error, that's the same thing in saying the consistency error is bounded from above by the corresponding, by this estimate times the function 1, and every point, or the vector 1, that's the vector which is meant here, and every spatial point, and from below by this number, which is the estimate times -1. So we can sandwich then the error between these two functions, and by means of this property we can then come to the corresponding estimate then of the error. Okay, the same thing we can do here, and so we have to have a consistency error in L infinity of the order alpha. We have to have this requirement which gives us the transfer of the maximum principal inverse monotonicity properties of the matrix AH to the matrix CH. It was this requirement. We need, of course, all the smoothness for the corresponding estimates. And then we get out that we have here an L infinity estimate in the corresponding order of convergence and in the corresponding order of convergence in time, because that is what we have done right now. We have estimated the overall consistency error now with these two terms here. So that means if we know more, if we know enough to ensure the inverse monotonicity, we can even go to L infinity estimates. Okay. Now, final step, finite element method. We will not be able to do this right now. Okay, but we should start. Okay, we should start. In the finite element method, as we know, everything is much simpler and much nicer and much more natural, because we don't have to deal with strange vectors and evaluate functions which maybe are not evaluable, and we have to take strange assumptions that we can do it. We have well-defined spaces where everything works, and that's it. And in this sense, now we are going back to our spaces in the finite difference method. In this sense, this is now a clear-cut general analysis now. We have our underlying function space V. We have the discrete space VH. And of course, our theta step method gives us a sequence, a time sequence of solutions which are functions un of VH. Okay, so we need, of course, also here a certain regularity in time, and that would be the regularity we will need to deal with the spatial discretization error which comes in. You might say there's also a lot of requirement here, being 2 times continuously differentiable in time with values in V, as in our case a subspace of WH of omega, but that's it. The proof now works very similar to the proof we did for the semi-discrete case. In the semi-discrete case, we put together the Ritz projection and estimated the 2 parts, and then we and this we do here the same, exactly the same. So we want to estimate. It's again an L infinity. We have to see which norm comes out. L infinity something estimate. So we look at the time levels Tn, compare the exact solution at Tn and the approximate solution at Tn. We bring in together, we put in, by subtracting and adding, the Ritz projection. So we have here an error term in the discrete space, as we dealt with already. And here we have it's now ordered the other way around, as in the semi-implicit case, we had the parts the other way around. Therefore, I pointed at the wrong one. So we have here the sorry. We have here the discrete part, the theta n, called theta n, but the notation is the same. So this is a part we have to do something with. And here we have the part rho Tn, which is just the deviation between the exact solution and the Ritz projection at this fixed instance of time Tn. So this term we have an estimate immediately. So either we leave it as it is in the first version of the order of convergence result, and then we only have to know how good is the Ritz projection. We have to know how good is the finite element method in the stationary case. So here we have already the corresponding order of convergence. of course requiring that u of tn has the regularity for this order of convergence. So the procedure now is the same as we had it in the semi-implicit case, namely to derive a discrete evolution equation for the theta n with some sort of the rho of t in the right-hand side as the forcing term. Because for the rho, for the Ritz projection error, we know already something. And then we are in a situation to estimate the other part of the error too. Okay, let's see how the computation works. Okay, this is now maybe not an optimal notation because we have to distinguish between the thin theta, which comes from this error term we are looking at, and the thick theta, which is the one from the theta method, but I think they are distinguishable. So what do we have? So we try to write down an equation for maybe fix this page, then we see the definition. No, what's this then? See the definition. So that is the assertion. So we would, or let me put it the other way around. We would like to have a formula for this part here, because this is, so to speak, our discrete equation for which we have already developed stability results. And this stability results we would like to apply, and in the end we would like to have a nice thing which we can further estimate. Let's see what we have. So we have here, of course, the Ritz projection, and we have the exact solution. And here we have the Ritz projection, and we have the exact solution. So in this first step, only the definition is plugged in. Okay, then we go further. Here we keep the first term, and now we substitute this term by this term. But this is just the notion, the definition of the Ritz projection. That this part is equal to this part is just the definition of the Ritz projection. That's what the Ritz projection does, that r times u minus u under the A bilinear form with some test function v is equal to 0. Okay, so, then we are here, and now we have to go on with this part, and this is Bn plus theta. What is Bn plus theta? Now we had to go back a few pages to see the definition, and that is the exact solution. That is just the right-hand side. Why do we the right-hand side of the discrete equations, which of course is fulfilled here by the discrete solution. So this is just the defining equation for the capital U of n. So the B is nothing but the evaluation of the right-hand side at the corresponding intermediate time level. No, it's not at the intermediate time level, it's the convex combinations of the intermediate time level. And that means for the exact solution, then for the exact solution, this is correspondingly fulfilled, meaning that we can substitute this part now by this part here. Why? What is the difference? What do we have here? we the only difference between concerning this part here, this part also appears in the corresponding, yeah, it's maybe too much to explain it like that. Then maybe I have another version which is more clear. It's a little bit too short here. How is it here? Here's the proof maybe I should have done, but I didn't do anyway. Yeah, the transparencies are not optimal, I have to admit. Sorry, maybe. Okay, we do it differently. Because actually I should have gone already because I have to see a doctor, apparently. We do this proof again next time, maybe on other material.